Okay, so in this video we're going to do kind of a little bit of a tricky proof. I mean, it's not that tricky, it's just like for me it's a bit tricky because there's a lot of ideas coming together. And so this time we're doing the argument principle. And it says that this integral, 1 over 2 pi I, over a simply closed contour, which means it's like simple, that means it doesn't self-intersect, and it's closed, so it doesn't have two endpoints like this. So it's simply closed. For example, this would be simply closed. This is a typical way people draw it. And we want f to be analytic everywhere on this contour. And we want it to be meromorphic on an open set U containing this contour. Then this holds. The integral of the complex derivative of f over f dz over that contour is z, which is the number of zeros of this function, minus p, which is the number of poles of the function. So how does the proof go? So let's have a little bit of an outline of what the proof looks like. So the first step of the proof is the product rule. Okay, so normally we see the product rule as f times g prime equals f prime g plus f g prime. In this case, we want another version of the product rule, which is just this, but we assume f and g are non-zero and divide through by them. And we see that the g's cancel and the f's cancel. And kind of, if you notice, it's like we had f times g, but then it somehow became f plus g somehow, right? So what we've done is we took a product and turned it into a sum. And this is the first idea. So this is idea number one. It's a bit messy. Maybe I could just write it down again. The idea number two would be the Cauchy-Gozart's theorem. This says that if f is holomorphic in some open set U, so not meromorphic like in the argument principle, but holomorphic as in it doesn't have any poles, then the integral over a simply closed contour in U of f of z dz is 0. First thing, second thing, and we have one final thing. We need Cauchy's integral formula. So number 3 is the integral formula. The integral formula says 1 over 2 pi I, some holomorphic function again, so just like in Cauchy-Gozart, we have a holomorphic function. We divide it by z minus, call it a. Z minus a, where a is some complex number. Then this is dz, where a is inside this c, inside the contour c. So if c is this contour, let's say, then a is somewhere inside the contour. This is a. And then this is equal to f evaluated at a. It's kind of magic, right? It's kind of a magic formula, Cauchy's integral formula. It tells us that just by integrating around something very similar to a function, we can actually get the value of the function at a point. Okay, so how do we proceed? Well, going back to the argument principle, because f is a meromorphic function, it has some zeros and it has some poles, we can write it as some function g times a product of zeros. I'll call it r for roots, because if it was z, then it would be a bit confusing because z is the variable we're using. Z minus the root. So this is all the roots including multiplicity, right? If it was, if f was equal to something like x minus 2 or something, x minus 2 squared, then r would be 2 twice. We'd do two separate times instead of just once, and then divided by the product over the poles of z minus p. And you might ask, well, are you sure we can do this? And we can, because it's kind of by the definition of poles, we can use limits of the function f by just looking at small intervals around the pole. So if we know the pole is here, we can find some open set where it's analytic everywhere except that pole, and then we could just remove the pole by multiplying by something of this kind with the appropriate power. So let's go back to this. In this case, we've pulled out all the roots and all the poles, and the function we have left over here is holomorphic now. It's not meromorphic, it's holomorphic, and it has no zeros. Okay, so now we've had the setup. Let's actually get on with the thing. So f meromorphic and g holomorphic on some open set U, and C is a simply closed curve in U, and F analytic on C. Something I forgot to mention before is that we want F to be non-zero on C because we're integrating F prime over F, and if F was 0 we would have an indefinite integral. So sorry about that, hope that makes sense. Okay, so first of all we want to write this in a different way, and we notice that F is G product over the roots, and using that trick we had before, if we have some product FG, then we can write it as a sum like this. It turns out it also works if we take the quotient. So if we did F over G, then this would just become minus. Sorry, this is G. This is F. Okay. And so we can work out that F prime over F is equal to G prime over G plus the sum over the roots of the derivative of this part, which is just 1, over just this, so Z minus R, and then because we're dividing now, we subtract the poles, derivative of this 1 and Z minus P. So using this trick, okay, we're basically just substituting this into here. So let's actually do that there, although we might have to carry on down here in a bit. So we have 1 over 2 pi I. Okay, so this part, because integrals are linear, we can just do each part one at a time. G prime over G plus, over the same contour, sum over the roots, 1 over 2 pi I, 1 over Z minus R, and minus 1 over 2 pi I, 1 over Z minus P. Oh, don't forget the integral. That's a bit messy. So we know that this function in here, G prime over G, based on this, on the contour, we haven't really done anything to G. This part doesn't have any zeros on the contour C. So if we just bring it over here, we're just multiplying F by another analytic function, and the product of two analytic functions is analytic. So G we know is analytic on C, and that means we can just differentiate it, and that's fine. And the ratio of two analytic functions is analytic as long as the denominator is non-zero. And G is non-zero on the curve C because F is non-zero on C. And so by Cauchy-Gozart theorem, we're integrating a analytic function over a closed contour, a simply closed contour, and by Cauchy-Gozart, this is 0. Okay, now we want to just write this part out again. Now for this final part, what we need is Cauchy's integral formula. We're going to use Cauchy's integral formula with the function. Well, Cauchy's integral formula, let's just quickly write it out. What happens if we say h is 1? We can do that, that's no problem, because we just need h to be holomorphic on some open set, and 1 is just a holomorphic function everywhere. So if we set h as 1, then we get 1 is equal to 1 over 2 pi I 1 over z minus a dz. And we see that it's 1 regardless of what a we choose. So we just got what we wanted. So over here, this entire thing, so okay, I kind of didn't explain what we wanted. Anyway, what we wanted is to be able to count these, how many r's there are, how many roots there are, and how many poles there are. And to count them, we would like this whole thing to be 1, right? And just now we used Cauchy's integral formula to show that it is 1 if we set the function, usually it's f, but because we're using f for something else, I used h. And if we set h as 1, then Cauchy's integral formula gives us this as 1. And so this entire bit goes to 1, this entire bit goes to 1. And so now we're summing 1 over the roots. So that just gives us the number of roots. So that's Z. And now we're summing 1 over the number of poles, and there's minus here, so minus number of poles, and we're done. So it did require a lot of different things, but actually it wasn't actually, once we put everything together, it was actually not that difficult. Okay, so hopefully that made sense. Thanks for watching. See you next one.